Hi, my name is Emily Weber. I'm a machine learning specialist solutions architect at Amazon Web Services, and today we're going to learn about deep learning containers. Let's get started. This is your deep dive. Wait, guys. The audio enhancer isn't working? No. All you need to do is update to the latest version of PyTorch. I saw it come in a couple weeks ago. And it's easy. We're just going to point to the latest container. Wait, we're not even running in a container? Wait, we're seriously running that script blind. Yeah, okay, that's why we're having problems. We need containers. So, as we come to find out, in computer science, in software development, in machine learning development, containers are a useful thing. Containers are a way that we can define our environment, we can define our operating system, packages, software, get everything really nicely wrapped and ready to deploy. That means we can avoid software dependency issues, environment issues, all sorts of things. Now, containers are going to hinge on one thing, and that's called Docker. So Docker is a super useful technology, and as we're learning about containers, we want to get more and more comfortable with Docker as time goes by. So your first step to working with Docker is to make sure that we have Docker installed. So whether we're installing that manually on our laptops, or if we're using that from a notebook instance, or if we're wrangling it in Studio, we're gonna get our hands on Docker in some capacity. Once Docker is installed, the next thing we're gonna do is bring in a base operating system installation. So whether we're using Ubuntu, Linux, any other flavor of operating system that we prefer, we're gonna point to that within our Docker file. So when we're just gonna create our Docker file, the next step is to point to some base operating system definition. Once we've got the OS set up, the next thing we're gonna do is install software packages. So whether you need pandas, numpy, scikit-learn, TensorFlow, MXNet, R, really any software package that you require, just go ahead and install that directly in the container. You see that run word? So we're gonna write run, and then any line we prefer, right? Pip install, conda install, any type of package you need, just go ahead and install it there. The next thing we're gonna do is copy our code into that container. So when we're developing our scripts locally, Docker is gonna handle that sort of logical jump, if you will. So we're copying from our local environment into the Docker container, right? Into that environment that we're building. And then our next step is to basically run our script. So we're gonna define this entry point, and then the entry point is the primary code that we're executing, right? So the script that we're utilizing, any arguments that we have for that script, any other custom ways that needs to be executed, we're gonna define it in that Docker file. And so that's how we build a container. And now you're gonna ask me, hey, this looks great, but are you saying I have to build this container from scratch every single time I'm trying to do this for machine learning? Unfortunately, the answer is no. Under no circumstances should you need to do that. So at AWS, we have more than 60 deep learning containers across 5 software frameworks. We update those things hundreds of times a year. So let's check it out. So a deep learning container is a pre-built image for TensorFlow, PyTorch, MXNet, Hugging Face, and AutoGluon. So 5 software frameworks. And then you can point to different versions of that, different versions within Python 2, different versions within Python 3. Some images are for training, some images are for inferencing, and you can use those in a variety of ways. The screenshot that we see right here is actually extending that base image. So in that top line of the Docker file, we're pointing to that pre-built PyTorch 3.6 image. So we're pointing to that image, then we're extending it with our own code. And so again, these deep learning containers are available in every AWS environment. They're fully available for customers to get started utilizing. And you can read all about them online. So our GitHub repository is fully public, AWS/deep learning containers on GitHub. Pro tip though, if you subscribe to the repository, which I have done, be prepared to get a lot of email updates. The team is updating these containers, I'm not exaggerating, hundreds of times a year. And so you will literally get notifications every day for all of the development that's happening. So the next question is, what can I do with an AWS Deep Learning Container? The good news is there is a lot you can do with an AWS Deep Learning Container. So many individuals are familiar with Amazon EC2, right? They're familiar with this concept of scalable elastic compute, where you can just get our hands on some compute that's in the cloud. Now, EC2 and deep learning containers go hand in hand. You may have heard of something called a deep learning AMI, right? The deep learning Amazon machine image. Essentially, when you're in the AWS console and you're trying to launch an EC2 instance, you can do that using the deep learning AMI as a base. So you can just launch a deep learning AMI, hop into that thing and start running your code. Now, a step above that are even more managed versions of essentially that core concept. So the frameworks themselves, specialized hardware, specialized optimizations that exist, and those are present, again, in the form of the deep learning containers. A step above that are actually the container services. So if you're trying to run on EKS, on ECS, on Fargate, or even on Lambda, all of these are going to start with a container. They're going to start with this core object, right? This core executable byte that we're defining. We're going to launch that in the Elastic Container Registry. So we're going to create this Docker image. We're going to push it to ECR. And then once it's registered within ECR, it becomes fully available across the rest of the container services. The essential idea is that once it's, again, registered within ECR and ECS, it's much easier to use across the rest of the services. What we're actually going to focus on today is that layer above that, even one more step, and that is SageMaker. So SageMaker is this fully managed machine learning service that you can learn all about. And today we're really going to focus on the deep learning containers within SageMaker. So containers for developing, actually. So for developing your Jupyter notebooks, containers for running training jobs, and then containers for hosting. Now, the question is, why do I need this thing? Like, what's the core value add that these deep learning containers are providing? So the first value add is that writing your code in a container and writing your code in a deep learning container lets you run your code on the cloud, right? At the end of the day, when your code is sitting in a container, you can get your hands on more compute, you can deploy it, you can run larger scale jobs, you can run jobs on a trigger, you can run jobs in a queue, you can run jobs in batch, you can run tuning, you can optimize your models. There are, limitless possibilities. You can even extend these on premises using ECS and EKS anywhere. So for hybrid applications, you can extend those with the container services in anywhere mode. Step one. Step two is using these pre-built containers helps us avoid that time-consuming process of building the base image. So you saw those steps we went through to define the Docker container. That last step is calling Docker build. And Docker build is frequently a very time-consuming step, depending on how many frameworks we're pointing to, how much software we're trying to package in there. Just calling that pure Docker build process can be very time-consuming. And so when we're using a pre-built image, we're literally just avoiding that, potentially 5-minute or more wait time where the container is building. So we're just avoiding that. The third reason why it's valuable is that when we are deploying on a container in a consistent manner across organizations, across teams, across projects, it helps our development environment be more robust. It helps our applications be more robust. So as we learned earlier in the audio enhancer failed experiment, essentially when you're using containers to deploy your content, to train your models, to enhance them, it makes the consistency a lot easier, which in turn helps your teams move faster. And the fourth reason to check out the AWS Deep Learning Container is that all of the software frameworks have optimized versions that AWS is developing and managing. So those hundreds of updates per year that AWS is crunching out for TensorFlow, for PyTorch, for MXNet, Hugging Face, and AutoGluon, all of these actually come with AWS-specific optimizations by default. So pointing to the latest version of Data Parallel, Model Parallel, using Neo for compilation, working with the rest of our communication primitives. There's a whole host of optimizations that are specific for those frameworks, in particular on AWS, so they're going to run faster and they're going to be more performant. So those are the 4 reasons why. And now let's check out some of the options. So the first view that we're seeing here is basically using the deep learning containers for training. Now in this case, we're pointing to PyTorch, right? And so we're setting up a PyTorch object. And now this is obviously in SageMaker, right? So you can imagine we're sitting inside of SageMaker Studio. So we're in Studio and we're importing this PyTorch object here. Now what's going on? This PyTorch object is pointing to a pre-built container. So it's literally pointing to the PyTorch containers just by virtue of sitting in the SageMaker SDK, right? From SageMaker.PyTorch, we're gonna import PyTorch. So we've got that object imported and instantiated. Then we're gonna bring our own deep learning models into that container. So any custom projects we're working on in TensorFlow, in PyTorch, in MXNet, whether we're working on projects that take, tens to hundreds of billions of parameters, or run on, 1 to hundreds to tens of thousands of GPUs, all of those we're gonna be able to point to, again, using this PyTorch concept, this PyTorch object, specifically the deep learning container for it, and then the entry point. And that's this guy. So we've got our script set up. We're pointing to the version of our framework, so 1.0, and that's just the version of PyTorch that we care about. We're setting up our cluster config, all sorts of things, pointing to our input data, and then we're gonna run our job. And so same flow as usual, those instances are gonna come online, our process is gonna run. So the images you see down here, the logos, those are different estimators and different containers that are available within SageMaker. So today, again, we're talking about PyTorch, TensorFlow, MXNet, and sort of the deep learning containers, but SageMaker has many others, right? You see all the ones that are available. Also, when you are coming across a case where you need the absolute latest push, and there just doesn't happen to be a container available, or maybe there's a conflict, what you can do in this spec here is bring any custom requirements in this requirements.txt file. So just set up your list of packages that you want to pip install, get that defined in your requirements.txt, and then we're going to park that in the same directory here. So either in just this base directory, or you can point to a directory and drop it there. So in any case, we're using the deep learning containers to train very large or very small jobs, or somewhere in between, on SageMaker. Now, the next way you can actually use deep learning containers within SageMaker is a couple fold. So one, the deep learning containers are actually available already through SageMaker Studio. So within Studio, when you're turning on kernels, when you're launching a TensorFlow kernel or a PyTorch kernel, what's actually happening is you're pointing to a deep learning container. You're pointing to the container for that framework version. So they're available by default. You can extend these using your own operating system, your own software requirements. You can extend these and then build new containers on top of that. Attach those to your Studio domain, and then they're going to show up within Studio. So effectively, if you're building, say, a platform for multiple users and you want to expose complex software package requirements to them, you can just attach an image, right? Just build your image, import from the DLC base, and then expose that via Studio. And then the next view here is, of course, training the largest, fastest deep learning models with the deep learning AMI. So again, model parallel and data parallel are both available by default within the deep learning container. So if you want to use optimized, again, communication primitives or optimized data sharding or model sharding techniques, all you need to do is bring your own code into the deep learning containers and then just modify a couple configs. So you'll point to our client, but actually use the majority of your distribution code, and that's going to be fully available. And then the last one, obviously, is hosting. So when you're taking a model that's trained somewhere and creating a real-time API, you can use the deep learning containers as your base. So now let's check it out as a demo. So you'll notice we're in SageMaker Studio. Right, I've got my AWS environment over here. I've got Studio set up. I'm sitting in US East 1. If you're familiar with Studio, this should look very normal. There's nothing special going on here. We've got our data widget over here. I'm in the SageMaker examples, right? So I'm going through the SageMaker examples repository. We're looking at Python, SageMaker Python SDK, and we're in PyTorch MNIST. So that's right here. So again, PyTorch MNIST. And we're checking this out here, PyTorch MNIST. And there we go. I'm going to close that out. And so a couple things. So if you are going through this at home, you'll notice that you do need to run this first line in the examples. So the example notebook is going to come in with this first line to just make sure that you have the right Torch Vision installed. Go ahead and run that line and then actually restart your kernel. So run that line, restart your kernel. You are also going to want to install IPy-widgets. So I love conda install. So I'm going to go ahead and conda install IPy-widgets. And if you're doing this in your notebook, just throw that -y at the end of it, right? When we're installing things, you can just add -y in the notebook context, and it's a lot easier. You'll notice that the kernel we're using is PyTorch 1.6, right? So we're using the PyTorch-based deep learning container. I'm sitting on my T3 medium. And let's keep cruising. So we're going to set up our SageMaker session like normal, right? We're just pointing to our SageMaker session. We've got our bucket teed up here. I'm going to download a data set. Actually, so when you run through this example, you can download it, no problem. My training job actually broke, so I had to modify the training job to re-download the data set from within the training script, which was fine, but the example notebook does come with this. And so we're going to set up our inputs. So we've got our SageMaker session that's just pointing to our data sets. And then we've got our training script set here. And so this line here is just printing out the model file. So the model file is over here. And let's actually view that via the browser. So I'm going to go down, and it's just in the same directory here, mnist.py. So let's look at that. So mnist.py. So we've got lots of imports, right? We're importing all these objects from Torch here, setting our logger. We're just going to define some generic neural network here. A couple convolutional layers, some dropout, feed forward, nothing crazy. Got our forward pass here, more dropout, returning the softmax. Life is good, nice and easy. So here's a function to drop that in that data loader. And this was the part where I had to add in download equals true. So the datasets.mnist from Torch Vision, right? So that's coming in from here. You know, I was able to get it to work using that download equals true. And so I would recommend folks check that out. Pointing to our data directory. If you're going through any troubleshooting, just always remember you can type in print statements, right? So when you're printing out various objects, various directories, locations in your training script, just go ahead and drop in a print statement there, write it to standard out. It's going to get captured by CloudWatch, and then we can view it there. So we're going to return this data loader, do the same thing for our test data. Got this average gradients process, and then the training loop. Method here for if it's distributed, setting our world size, all normal things here, using that logger package. Train and test loaders. Life is good. We've got our model set to the device. And then we've got our epochs, right? So we're going to loop through our epochs, set model to train, walk through our batches here, and run our step, right? And so this is nothing new. Obviously, this is a very generic, very simple process. And then we're going to set if name equals main. So like typical on SageMaker training, we'll just use this to start our execution. Definitely, if you're just getting started with training on SageMaker, you really want to be good friends with that argparse. Like we use argparse all the time. So definitely make sure you're comfortable using that. What I honestly do is I use this default a lot. So I just pasted what I need in that default, but then you can add changes here. So we've got parser set up, and then we're just going to call train. And so again, this is fully customizable. Do whatever it is you need to do, write whatever code you need to write, get it done right in there. So that's our training script. And now we're going to take that training script and we're going to put that into the container, right? We're using that pre-built PyTorch container, and the container is going to run on these instances. So here we're using two C5 2XLs, defining very preliminary one epoch, just for the purposes of the demo here. And then we're going to call estimator.fit. So this is all normal, right? We're running this process here, printing out the training environment. We're going to view the environment variables. And as usual, we can see that in the console. So if I go back over to my AWS page here, I'm going to click on this tab on the left. I'm going to go down to training. So under this training tab, I'm going to click on training jobs. So training jobs. Then I'm going to go over to PyTorch training, this one. We'll give that a click. And I'm going to close this out. And so this view has all of the metadata for our job, right? All of the images that we used. So here's that deep learning container image that we're using, the hyperparameters, my data set in S3, my data replication type, my checkpoints, data output path, all sorts of things. I can view the logs, right? So I'm going to pop over here, take a look at the CloudWatch logs. And so we have these log streams for both nodes in this cluster, right? So we have two instances that are up here, running through that first epoch and then calling it quits. So that's the log stream. And then the last thing to check out is just the output path, right? So we're pointing to our artifact right here, and that's the trained model that comes in as a result of this process, right? And so this is out here in S3. So we're going to copy the S3 URI, and then we can cruise back over to our notebook. You know what? I'm just going to minimize this here. And then let's zoom back up. And then just for fun, we'll just do an AWS S3 copy. Helps if I type in P. There we go. Great. So now we have the model artifact. Done and done. Now the last step we're going to do here is, again, use that same deep learning container, but this time we're going to deploy our model. So we have this estimator object that we created above. That estimator, importantly, had a training job attached with it. So when the training job completes successfully, then we're able to do this sort of really nice one-line model.deploy. If we don't have a training job, then you just want to bring in a pre-trained model, right? Something you trained in your laptop, trained on-prem, load that up into AWS, make sure the directory for it is appropriate, and then still run model.deploy. Bring your own inferencing scripts. Life is good. So we're going to set up this predictor. And then we're going to point to some of the raw test data for MNIST and then get some predictions. And so the predictor.predict line is happening here, right? So remember, we're saying that predictor is this variable that is estimator.deploy. And so we can also point to the predictor, say like from our Lambda functions. When we're building our application, in our Lambda function, we can point to the predictor in the same way. Just won't call .deploy, you'll just point to the name of it. But so in any case, we'll call predictor.predict, we'll get our responses back, and bam, here we go. So those are coming in hot. I actually deleted my endpoint already, but the good news is that every time you create an endpoint, you're also by default creating what's called an endpoint config. So your endpoint config sits right over here. So that endpoint config is pointing to your model. So it's pointing to the model, and it's basically setting up the instances and the traffic that you want to use for that model. So that's all fully available. If you want to apply that to an endpoint, you just apply it, and you'll turn on a net new endpoint. So that's the demo. And so the net here is that we can actually use the deep learning containers to deploy your models pretty much anywhere on the cloud. So the answer is yes, right? You can build your deep learning containers, you can build those on SageMaker, you can build them on your laptop, you can build them on Studio, you can build them on premises, you can build them in a pipeline, you can build them, really anywhere you can get your hands on a computer and set that up to the cloud. It's just that we typically find that purpose-built managed services tend to be easier, but it always just comes down to your use case and the feature set that's available at that point in time. So a couple pro tips just to wrap this up here. So the first one is tagging in ECR. So as you're building your containers for training, for deploying, as you're pushing those into the Elastic Container Registry, you want to develop some tagging process. And as is common in software, you can say version 0.1, right? 0.1.2, 1.3, right? And so within your team, you want to establish some tagging process so that you're aware of the different varieties of code that are available in your containers. Pro tip number 2 is to extend our containers, right? So when you're working with custom content, A, you don't have to build your container from scratch, but B, when you have, complex content that you're developing, it can be a lot easier to just extend our container and package up your own Docker container. Sometimes that's just easier, depending on exactly what it is you're trying to do. So extending our containers, and then definitely check out the anywhere capabilities. Like if you're trying to, deploy to a gaming application that's hosted on premises, or if you're involved in an enterprise migration, or if you're serving, a model to content producers on-prem, check out our Container Anywhere services, ECS, EKS Anywhere, and play around with the deep learning containers. And so with that, I hope you enjoyed our time together. Thank you very much and have a great day.